Hello and welcome to the third lesson of Area Study 2. Today we'll be taking a look at transformers, which in a sense is the application of flux. So what are we going to do? First thing is we're going to look at alternating current and alternating current power. We're going to then take a look at what the transformer actually is before applying our knowledge of circuits with the turns ratio. So what is alternating current? It's produced by something called a generator, and that's something that we learn about a little later on in this unit. And what happens is the power is produced in a shape that looks like a sine wave, or a cosine wave for that matter. We consider the current and the voltage to have an average value called the root mean square, or RMS. And that's the value that we're going to be using predominantly for our calculations. Because the current keeps changing, it means that the magnetic field associated with that current flow is also changing, which is really the core part of the transformer. So what is RMS and peak voltage and current? So these two formulas here show that there's a relationship something to do with root 2. And the reason that it's to do with the square root of 2 is a little bit complicated for this course specifically. But in a sense, it's just pretty much the average value of a sine wave. What we can see from this graph is that there's a peak voltage and peak current. And as we move along through time, that flips direction, and then it keeps flipping back. So this sine wave would go on and on and on forever. And that is the peak to peak voltage or current. If we're just talking about the peak current, it's only what the voltage and current is in one direction. And those two terms, so peak and peak to peak, I'll to draw that, this would be the peak voltage or current, whereas this would be the peak to peak voltage or current. And that's quite important because there's usually a question or two in the end of year exam on this specifically. Here we have a diagram of a transformer. And in this, you can see that there are two coils and there's some wire wrapped around each of them. Every coil will be similar to this. It'll have two coils and it'll have differing number of wires or loops around each coil. And that's really important because, as we see later on, that will give us a representation of the turns ratio. Every transformer obviously has a core, and part of that core is made out of what's called soft iron. Now, you don't really need to know the difference between soft and hard iron, if you were to call it that, but pretty much it has to do with the formation of the electrons and the ability for current and magnetic field to travel through it. Finally, there's got to be a power source, otherwise our transformer is useless. It'll be on one of the sides. In this case, I've put it on the left-hand side because that's where the current is coming in. We always consider a transformer to be ideal, which means that we never lose any power due to any kind of resistance within the coil. Now, in real life, there is no such thing as an ideal transformer. Nothing is ever perfect, and we always lose some energy in this process. So, now that we know a little bit about the transformer itself, how can we apply Lenz's law? As the current in the left-hand side of that coil changes, because that's where I've said the current comes from, the magnetic field that is induced by that current, if you use the right-hand grip rule, that will keep on changing because the direction will keep changing. And so will the magnitude for that matter. Because iron is highly magnetic, it conveys this change in magnetic field to the secondary coil. And in the secondary coil, this would be the change in magnetic flux. because there's a change in magnetic flux, using Faraday's law, we can say that there is some kind of induced voltage being given off, I suppose, or induced from that change in magnetic flux. And using Lenz's law, we can find that direction. That's why there's going to be a current that comes out of that secondary coil. What I should also add before we get into step up and step down is how this change of flux actually works. And the way that this flux works is, let's just happen to say that our current does go in this way over here. So it kind of goes up around like that. That means that using our right-hand grip rule, we'll curl our fingers around that coil, and we find that our induced flux is going to be going up around this way. Now, that means that when it comes around to this second coil, we have an induced magnetic field that's increasing. For the sake of this, we'll say it's increasing. So let's say we start from zero current, like we do in a normal sine wave. So at this point, the current is increasing. So the induced current, the induced magnetic field is also going to be increasing this way, which means that our our induced magnetic field in the secondary coil is going to oppose that change. So it's going to go that way. We apply Lenz's, the right-hand grip rule here, and what we find is that the induced current is going to be coming around like this. Therefore, finally, our induced current in the secondary coil is going to be flowing out this way. Now, obviously, not every transformer is identical in the way that their coils are made, which means that if you are given a question, you have to tell quite closely and have a good look as to which way the wires are going around that coil. Now we can move on to step up and step down. So you may know that the coil that's connected to the power supply is called the primary coil, because that's where our power comes from, while the output's called the secondary coil. That's not too difficult to note, but a surprising number of people get it wrong. So make sure that you're always identifying where that power source is, and therefore where the primary and secondary coils are. When there are more turns in the primary coil, then it becomes a step-down transformer. When there are more coils in the secondary, more turns in the secondary coil, it's a step-up transformer. And when we're talking about step-up and step-down, what we're talking about is actually the voltage. So the voltage will step up, it'll go up in a step-up transformer, and in a step-down transformer, the voltage is going to go down. The turns ratio is just that ratio of turns the coil from the primary to the secondary. If, for instance, you are given a question, you should always make sure of these 3 points kind of in order as well. Don't mix up which ones are the primary and secondary coil, and make sure that your answer is logical. So if the question says it's a step-down transformer, then the primary coil is going to be more than the secondary coil, and vice versa is true. You only kind of look at transformers relating to the input and output. We don't have to really worry about what's going on in between, but you'll get to questions where there are more than one transformer. So only consider one in isolation and then move on to the next one if you are given two in a question. These are the formulas that are important to know. So you may want to take these down. These are also on the formula sheet. So if you don't feel like taking them down, you don't necessarily need to, but you should, just as good practice. So in a step-up transformer, our current's going to decrease and voltage will increase. Step down, the opposite's true, and the power in both the primary and secondary coil because it's an ideal transformer, it's going to be the same. Let's apply our knowledge with a practice question, a 6-part practice question, I believe. So yeah, let's have a go. So an AC power source provides an RMS power of 30 watts and the voltage is shown below. Set the frequency of the AC voltage as part A and find the RMS voltage as part B. 2 marks, separate questions, so a minute each, 2 minutes all up. All right, now that you've had a go at that question, what's the answer? Well, first one, very straightforward. 1 on the period is our frequency, which means that it's 50 hertz. Second question is also quite straightforward. But there is a big but. Always make sure that you use the values given to you and divide it by the square root of 2 or multiply it by 1 on the square root of 2 to get the RMS. So make sure you're always looking at where those voltages are and whether there's anything you need to do with them. So in this case, this looks like the peak voltage. So we divide that by the square root of 2 to get the RMS voltage, which is 7.07 volts. Find the RMS current and hence the peak current for 2 marks, 2 minutes. Off you go. All right, now that you've had a go at that question, what is the answer? Well, we use this formula. So the power, RMS power always, is the 2 RMS voltage and currents multiplied by each other. We know that the RMS power is 30 watts because it said so in the question, and we just found what the RMS voltage was. We can therefore rearrange to get an RMS current of 3 root 2, which is the same as 4.24 amps. The peak we multiply by the square root of 2, and you should get exactly 6 amps. Mark allocation, you get 1 for finding each of the RMS and peak values. Part D. Part of a circuit is shown below with an ideal step-up transformer with 100 coils on the left and 400 coils on the right. Find the voltage and current delivered by the secondary coil. And you could say, if you want to extend that question, it would mean the same thing though, delivered to the resistor. So that means the same thing, by the way. Worth 4 marks, so make sure you answer all parts of the question here. You have about 4 minutes to do it. Now that you've had a go at that question, we can go through the solution. First things first, we use the turns ratio. So primary voltage to secondary voltage is the same as the ratio of the turns in the primary and secondary coils. Pop in our values there, remembering that the power source is the same. This is the same question with that same AC power source. And we rearrange to get secondary voltage of 28.3 volts. We can also apply the turns ratio for current, and that will give us a secondary current, a current in the secondary coil of 1.06 amps. Mark allocation, you get 1 mark for kind of these 2 points, 1 mark for the answer, another mark for these 2 points, and 1 there for the answer. Second last question, sketch the graph of current out as a secondary coil for 1 period worth 3 marks, and it shouldn't take you any longer than 3 minutes. All right, hopefully you've had a solid attempt at this question. Let's go through the answer. So here I have everything that we need to answer the question. I have labeled my peak currents. So obviously plus or minus the same value. And the way that we get that 1.5 is we have to go back here, multiply 1.06 by the square root of 2 and you get 1.5. The time doesn't change at all, so that's something that you need to know when you're looking at transformers, is that the time, there's nothing really to say other than it doesn't change. An answer that is reflected in the x-axis is also fine, so if it looked something like that, that would also be a perfectly acceptable answer. Mark allocation wise, you get 1 for the shape of the graph, so it has to be a sine wave, either of the red one and the blue one. 1 for the value over here of 0.02, and then another one for the y-axis labels of 1.5 and minus 1.5. Last question, the AC power source is removed and replaced by a DC battery with an identical RMS voltage and current. Explain why the RMS voltage and RMS current through the resistor are recorded as 0. 2 marks, should not take you any longer than 2 minutes. You can have a go at that now. All right, now that you have made a good attempt, hopefully, at this question, we'll have a look at the solution. So the first thing that I've said is that as a DC power source, it should say, is not able to supply a change in current to any transformer, there's no change in flux. So as a DC power is not able to supply a change in current to a transformer, there's no change in flux. Apologies for that poorly worded sentence. I seem to have gotten a bit muddled up there. Anyway, by Lenz's law, there's no change in flux, and therefore there's no current and no voltage to be induced in that secondary coil. So remember, at the start, and in fact, go back to it, all the way back here, to go through all the parts of this. When I said over here that an alternating current means that the magnetic field changes, that's the key part that makes a transformer work. And we saw that again over here when we went through all of this. So you have to have a change in flux, and therefore the current that you bring in, a DC direct current, doesn't change, doesn't alternate. So that's how that works. With that, that is all that really needs to be said for this question. Just make sure that you understand the theory behind why it is 0. And of course, you're welcome to let me know if you have any questions regarding this. Final notes, make sure that you understand how they work, why you need a core that can conduct magnetism, so that's iron, the necessity of AC over DC power, make sure you know how to sketch alternating current, and how we represent transformers in different diagrams. What I mean by that last point is that in this question here, you saw that the transformer is represented by these diagrams, and now you can't obviously count the number of coils in each, so that's given to you in the question. With that, that brings us to the end of our lesson. We've gone through what I would say is a decent chunk of this unit. Transformers, generally speaking, make up the majority of the assessment for this area of study. And of course, there is the application of transformers when we look at transmission lines in the next lesson. Thank you very much for your attention. I hope that you found this lesson to be at least somewhat interesting and that you learned something new. If you'd like to get in touch, feel free to go to airlearners.com and you can find me on the tutors page. Thank you very much. I'm Noah Bajeo, and I'll see you next time.